Today we are going to discuss about nuclear magnetic dipole moment. Before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT123. This is my Insta ID. You can follow me on Insta. So now let's start. So now you see, if a particle, let us say it is suppose proton of charge E. So charge, charge of proton is equal to the charge of electron but opposite in nature. So I have written here E circulates in a circular path of radius small r with speed v, and the equivalent current is given by I is equal to E by T. That means current I is equal to Q by T. Q is the charge by time. Okay, so that means, so if we consider a circular loop, then suppose this is a charged particle with charge E, suppose, and it takes time capital T to complete one cycle, right? Then due to the motion of this charged particle, there must be a current which will be given by I is equal to E by, instead of this Q we're going to put E, and instead of small t we're going to put T, which is the time period here. Okay, so I have written in small I instead of capital here. So now let me copy this, cut it. So now you see, when a circular when a charged particle circulates, this circular loop behaves like a magnet. And so if it behaves like a magnet, then magnetic dipole moment is given by, if the area of this loop is suppose A and current through it I, then magnetic moment is given by I into A. Here this area vector A is, here you see area is pi r square, which is the area of this loop, right? And this r cap gives the direction along the area vector. So this area vector is always perpendicular to the plane of this circular loop. Okay, remember that. And the direction along a cap is given by a vector is given by r cap. So that's why I have written here r cap. And so this is what I have mentioned here. This is the area vector, and unit vector along the area vector A is r cap here. Okay, so hope you have understood this. Now you see, this is the magnetic moment here. So if we use this value of A here, then we get this result, and instead of I we have used this result. And then what we can do, you see, if this proton is, or the charged particle is moving with speed v, right, and to circulate once it takes time t, then this distance, that means the length of this circular loop is given by 2 pi r. So distance by time is the speed, right? So that's why we can write t is equal to pi r by v, right? So that's why this t is replaced by 2 pi r v, and so we have got this result, right? So hope you have understood this. Okay, now you see, if we simplify this pi cancels r square, gives r. So here we have got this. Now let's multiply m with the numerator and denominator, right? Then we have got this result. So mvr is the angular momentum, L, right? And angular momentum vector is written this way, right? mvr r cap, right? So hope you have understood this. So that's why we can replace this by L vector. Okay, and doing so we have got this result, right? This part gives the magnitude L, and with the r cap, r cap gives the r vector L vector, right? Hope you have understood this. So that means we can write this angular momentum is this angular momentum vector is like this. L vector is equal to L r cap, which is equal to mvr r cap, right? Okay, and this GL is the orbital gyromagnetic ratio for proton, and its value is 1 in this case. So here we can say that there is 1, right? If we assume that way, there should not be any problem. So similarly, this is the orbital magnetic dipole moment due to the angular, not angular, this orbital motion, right? So in addition to this orbital motion, there will be another magnetic moment due to spin, right? Due to spin, that means it is revolving in a circular path, and also it is spinning. Actually, electron, proton, these particles doesn't spin, okay? They do not spin, okay? But in order to explain the result, this of nuclear magnetic moment, so we used to, in order to explain those things, we used to assume they have also spin angular momentum, okay? In addition to the orbital angular momentum, right? So hope you have understood these things. But practically, actually, proton is very fundamental particle, right? So it cannot spin. Proton, electron, these particles do not spin actually, because you see, definition of spin, according to, suppose this is an object, if it is spinning like this, then we can say each and every particle of this object must be revolving in a circular path, okay? Proton itself a fundamental particle. There is no any other particle in it. So that's why we cannot say it is spin, okay? So hope you have understood this is the point what I am trying to say. So in addition to this orbital angular momentum, we also get spin angular momentum, which is given by this expression, and in this case this GS is the spin gyromagnetic ratio, and total magnetic dipole moment is given by this. So sorry, if I have said angular momentum, this is not angular momentum, it is orbital magnetic dipole moment, not momentum, okay? This is also magnetic dipole moment due to the orbital motion, and this is due to the spin, okay? So hope you have understood this. And the total magnetic dipole moment will be given by vector sum of this spin spin magnetic dipole moment and orbital magnetic dipole moment. And if we use the results of this and this one, then what we get this expression. And in a nucleus, there will be there may be more than one protons and neutrons, and to obtain the net magnetic dipole moment of the nucleus, we have to add the magnetic dipole moment of each individual particle, and adding we have got this. Suppose if the mass number is Z, that means it must contain Z number of nucleons. That means if the number of protons is, suppose just wait, let me change it. This is, instead of Z, let me take mass number is A, and if the mass number is A, and suppose Z is the just give me a second, let me write it correctly. So let me make a correction here. So mass number is, suppose, A, and number of protons is, suppose, Z, okay? Then number of neutrons number of neutrons will be given by A minus Z. The total magnetic dipole moment. Okay, then we have to change here. Okay, sorry, this is correct. This is Z, and this is supposed to be A. This is supposed to be A, because you see, let me tell you something. So this Gl is 0 for neutron. Okay, so that's why we do not consider here the neutron, only we take the protons only, right? So remember that. So let me mention here. Okay, sorry, let me mention one thing. Gl is equal to 0 for neutron. That's why in case of orbital magnetic moment, we don't use to consider the we used to consider the number of protons only, not the neutrons. Okay, so but here in case of spin, we used to take both the neutrons and protons. So now let me go to the new slide. Okay, this expression, let me make the correction here also. Sorry, this is this supposed to be A, right? This is supposed to be A. Okay, and so this can be written this way: Z into I is the total angular momentum I have taken here, and Z is the gyromagnetic ratio of nucleus, which is nothing but Gi is nothing but this, and so that's why we can write this way. And here you see we have multiplied H cut here and also with the numerator, then we have got this expression, and this term is called nuclear magneton. This is called nuclear magneton, beta n. Okay, this is called nuclear magneton. Okay, so this is the expression for magnetic dipole moment of nucleus. So hope you have understood this. Thank you for watching. See you in the next video. Bye bye.